In this video, we're going to talk about sequences, what they are, what a term of a sequence is, what the nth term of a sequence is, and then we're going to look at a couple of special cases called arithmetic and geometric sequences. I know it looks like it says arithmetic and geometric sequences, but it's actually an adjective. It's a particular type of sequence, so we say arithmetic. So we have the arithmetic and geometric sequences. And then we're going to have two objectives for you. After learning these definitions, I'll want you to be able to write out the first few terms of a sequence. Like I might ask you to write out the first 4 terms or 5 terms of a sequence, or I might ask you to find a formula for a sub n. Now this video is going to tend to be very abstract. This chapter tends to be very abstract, but it has a lot of practical application that we're going to see later in the very end of the chapter, in the sections on power series, Taylor series, and Maclaurin series, and polynomials that we approximate functions with using those series. This section is not about series, it's about sequences, which are building blocks for series. But I just want you to know in advance that we are building towards something that is very applicable in applications, in the sciences, in the real world. But first, it might not feel like that. So I'll try to throw an application problem in there occasionally, just to remind you that this has some meaning outside of math. But we're going to focus on the abstraction for right now. We're going to talk about the concept in general, and then know that these concepts in mathematics, they just tend to apply to lots and lots and lots of different functions that behave in similar ways. We get rid of the details in math, and we focus on like the overall patterns. And then we see all kinds of things in the real world that those patterns apply to. And this is one of those topics. So let's talk about what a sequence is. If you think of a sequence of events, or even the sequence of courses, the calculus sequence, calculus 1, calculus 2, calculus 3, you're thinking of a sequence in pretty much the same way that we're thinking of a sequence in this section. The only difference between this section and that everyday definition is that in this section we're referring to sequences of numbers. So we're going to say that a sequence is an ordered list of numbers, and we're going to be dealing with infinite sequences. So this is going to be an infinite, so it goes on forever. There are going to be dots at the end because I can't write them all. Ordered means the order matters. The first one's in the first position, the second one's in the second position, the third one's in the third position. If you mix them up, you put them in different positions, it's a totally different sequence. And it's a list of numbers. Sometimes people will say it's a function defined on the set of natural numbers. So natural numbers are counting numbers. It's represented in mathematics by this n with the double bars. 1, 2, 3, and so on. But sometimes we loosen that restriction. Really, an infinite sequence is just a function defined on a subset of the integers. I think this is what our book says, but then they say, oh, we can also add 0. It turns out you can also add -1 and -2. You can add lots of digits at the beginning, but we don't go from negative infinity to positive infinity with infinite sequences. We start at a particular integer, and then we keep going. So this is the textbook author's definition. And we're using Larson and Edwards right now. So Larson and Edwards define it this way. But technically, then they go back and they say, well, we could append a 0, or we could add a -1 or something like that there. So let's just say it's a function defined on a subset of the integers And integers are all your natural numbers, those natural numbers times -1, and then 0. But generally, the way these infinite sequences work is you start with a particular integer and then you move forward. So we're not going to go all the way to negative infinity. We're always going to move forward. So we might start at n equals -7 and then go -6, -5, -4, -3, -2, -1, 1, 2, 3, 4, 5, and so on, and we keep going. And just for your sake, for your notes, integers are represented with by this z with the double bars, and they go on forever in both directions. You get all the negative, I want to say integers, I'm using it to define integers, sorry. All these whole numbers, well, all the natural numbers but negative, 0, and then all of the positive integers, those are the natural numbers. Okay, so we'd start at maybe say -3, and then we keep counting forward. Now, instead of using function notation, so f as a function of n. When we're talking about sequences, we tend to write it with subscript notation. And we tend to represent sequences by lowercase letters. So we might say the sequence a sub n, or b sub n, or c sub n. And that n is referring to the term. So before I get into the definition of a term and then the nth term, let's look at an example. So this is called the Fibonacci sequence. You may already know it. Now this is a sequence that's not defined by a formula, but it's defined what's called recursively. The recursive definition, they usually give you values of a couple of terms in your sequence, a couple of numbers in the sequence, and they tell you how the other terms are related to those terms. So, okay, I'm using the word term too much and I haven't defined it yet. So let's start like this. A sub 1, that's the first number in our list, we call it the first term. For the Fibonacci sequence, that's 1. This is the first number in our ordered list of numbers for this sequence. So that's called the first term. For the second term in the Fibonacci sequence, it's also defined to be 1. So a sub 2 is the second term. A sub 3 is defined to be the sum of the last two terms. So it's a sub 2 plus a sub 1. So we just get 1 plus 1, which is 2. Now instead of writing it vertically like this, I'm going to write it the way sequences tend to be written. They tend to be written in ordered lists like this. So you use the sort of curly braces, and you start with a sub 1, then you write a sub 2, then a sub 3, and a sub 4. And the nth number on this list is a sub n. I've had many students say, what do you mean nth number on the list? If n is 4, it's the 4th number on the list. If n is 5, it's the 5th number on the list. If n is 10, it's the 10th number. So when a sub n is the nth number on the list, and these numbers on the list are called the terms of the sequence. And a sub n is the nth term. And what I just told you about it being the nth term, it works for most numbers. For n equals 4, it's the 4th. N equals 5, it's the 5th. N equals 6, it's the 6th. N equals 10, it's the 10th. N equals 20, it's the 20th. N equals 100, it's the 100th term. It doesn't work for 3. It's not the 3rd term. But you get the idea. If I'm starting with a sub 1, and that's the first number on the list, like that's the nth number. And I've got a whole bunch of numbers. So let's write out the Fibonacci sequence. I'm trying to recycle this old paper, but it's got too much bleed through. Alright. Just reuse old paper, I guess is what I'm saying. So for Fibonacci, a sub 1 is 1, a sub 2 is 1, and we write those on the list. And then you add the last two numbers together to get the next one. So 1 plus 1 is 2. To get the next one. 1 plus 2 is 3. To get the next one. 2 plus 3 is 5. To get the next one. 3 plus 5 is 8. To get the next one. 5 plus 8 is 13. And you keep going. 13 plus 8 is 21. And so on. This is called the Fibonacci sequence. Isn't that pretty? All right. Now this is, I said it was defined recursively, and that just means that instead of giving you one formula for the nth term, terms later in the list are defined in terms of earlier terms. So a sub 3 was a sub 2 plus a sub 1, and let's write this out down here. A sub 4 is a sub 3 plus a sub 2. A sub 5 is a sub 4 plus a sub 3. It's always the sum of the last two. Like that's how it was defined. You might say, how can I write that down in a formula? Well, we can't write a general formula down for this nth term, but I can write it down in terms of these first two, and then a formula for the next one after that. So this is a sub 1 and this is a sub 2, and I want a formula for the n plus 2 term. I'm going to take the n plus 1 term, n plus 1th term, and add the nth term. Now you might say, how on earth is that related to anything that we just did? Let's think about it. The nth term, that might be the 10th term. And then if n is 10, n plus 1 is 11. So that's the 10th term plus the 11th term equals the 10 plus 2, the 12th term. So this is a formula that's going to work to define a sub 3 is a sub 1 plus a sub 2, and a sub 4 as a sub 2 plus a sub 3, and a sub 5 as a sub 3 plus a sub 4, and so on. We keep going and we get this. So that is what's called the recursive definition of the n plus 2nd term, and I guess we need a restriction. This is for n greater than or equal to 1. Well, actually, I think that's fine, because we start with a sub 1 and a sub 2 gives us a sub 3. Okay, so that's one way you can define the sequence. It's in terms of other terms and a formula relating the terms. Another way you can define a sequence is in terms of, I'm using the word term so many different ways, I'm so sorry. We can define a sequence with a formula. So we might have something that looks like this. Now if I want to write out several terms of this sequence, well, I'm just going to substitute. It's just like a function, except instead of an x, we're plugging in an n value. And the n values are always going to take on positive integers, or at least it's implied that n starts at 1, unless they give you some other number to start with. So let me give you some notation before we start writing out terms for this sequence. Sometimes we'll just write a sub n as the formula for the nth term, but normally when we're talking about the sequence, we write it that way. This is the sequence a sub n. Sometimes people will write it out as a list, a sub 2, a sub 1, a sub 2, a sub 3, all the way through a sub n, and then keep going. So people might write it that way. And with both of these, it's implied that n starts at 1 and goes to infinity. Well, it's implied that n starts at 1 and goes to infinity here, and it's explicitly showing us that n starts at 1 here. Now, if you want to start at some other number other than 1, let's say you want to start with n equals 2 or n equals 0, you're just going to write n equals that number to infinity here. So maybe it starts with n equals -2 and goes to infinity. All right, so that's just notation. And again, if it just looks like this, it's implied that n starts at 1 and goes to infinity. All right, so somebody give me this formula and they say, let's find the first several terms of this. All you do is plug in the first several positive integers. So we're going to substitute n equals 1 here. 2 minus 1 is 1. And we're dividing by 2. A sub 2, you have 2 to the second here. I've got 2 squared minus 1 over 2 squared. So it's 4 minus 1, which is 3, over 4. A sub 3 is 2 cubed minus 1 over 2 cubed. 8 minus 1 is 7 over 8. And let's find the fourth term. These are numbers for a different problem, sorry. The fourth term is 2 to the fourth minus 1 over 2 to the fourth. 2 to the fourth is 16. 16 minus 1 is 15. And we've got 16. So let's write out the first few terms of this sequence. We've got a sub 1, that's 1/2. Then we have 3/4. Then we have 7/8. We've got 15 over 16. And you keep going. The nth term is 2 to the n minus 1 over 2 to the n. And you keep going past that. And that is our expanded form of this sequence. So you might see it written this way. And it's implied by context that n starts at 1. Or you might see it in this expanded form. Or someone might be very explicit. If they're not sure that you know it starts at 1, they might say, hey, start at 1. That's what that subscript means, and go to infinity. So there's 3 different ways of writing the same thing. But this time our sequence was defined by a formula. Okay. So we looked at sequences defined by formulas. We wrote out the first few terms of a sequence that were defined, a sequence that was defined recursively with the Fibonacci sequence, and then also one that was defined with a formula. I can't actually write out this list of values for the next sequence I'm going to mention, but any function on the natural numbers or a subset of the integers, it starts at a particular integer and just goes forward, that's a sequence. So here's another example of a sequence. So I might have the population of, let's just say the world population on January 1st of each year starting in 1900. So we might say that 1900 corresponds to the year n equals 0. Or no, let's do n equals 0. So 1901, that's going to correspond to n equals 1, and a sub 1 would be the population of the world on January 1st in 1901. And I guess we're going to assume it's 12 a.m. We're going to count the world population. That's what we're going to call a sub 1. And then a sub 2, that would correspond to n equals 2. That's in 1902. That's going to be the world population on January 1st at 12 a.m. in 1902. And so you just keep going. with different values of n, you're talking about a different year. A sub 80, that's the world population on January 1st, 1980 at 12 a.m. Now, I don't have a formula for this. There is no formula for this. We might be able to come up with a mathematical model that describes the population of the world on January 1st of each year starting in 1900 for the last 120 years. We could find a mathematical model and we'd have 120 numbers. And then we could project forward for what happens on January 1st in 2021 and what happens on January 1st in 2022 and so on. That's a sequence. It's not defined by a formula though, but it is defined on a set of integers, and I'm assigning to every integer starting with n equals 1 and maybe even n equals 0 if we wanted to. We could go back to 1900. I'm assigning to that particular n value a world population in that year. So this is a sequence as well. All right, so you can define sequences by lists of values, by formulas, or recursively. In this class, we're going to tend to define sequences by formulas, and occasionally we're going to look at sequences defined recursively. Lists of values are very interesting. Data looks like that, but yeah, that's not going to tend to be our approach. We're not going to tend to analyze data like that. We're going to analyze some beautiful abstract functions that apply in many situations, but that aren't as randomly generated as, say, a world population in a particular year. Okay, so we just talked about what a sequence is. Let me just go through this list again. This is my favorite definition of a sequence. It's just an infinite ordered list of numbers. The order matters because if I switch the population in 1901 and 1902, it's a different sequence. You know, the population in 1901 goes first, population in 1902 goes next, population in 1903 goes after that, and it has to go in that defined order. That's true for all sequences. Now, one of the formal definitions is that it's a function defined on a subset of integers, starting at a particular integer and then moving forward. That's so wordy that our textbook author says it's defined on the set of natural numbers, and then they loosen that. So I'm not going to use their definition because they don't even hold to their definition all the time. Just know that you're going to start at a particular integer and then increase by 1, and increase by 1, and increase by 1. And then rather than using this subscript note, or rather than using this f of n notation for this function, we're going to use subscript notation. So sequences tend to look like this. I might have a sub n, it's my sequence of a values, and b sub n is a different sequence, c sub n. And if I'm talking about the entire list, I usually put it in brackets like this. And if there's no superscript or subscript here, it's implied that n starts at 1 and goes to infinity. They give you a subscript, well, then you know where to start counting. Okay, now some more terminology. These numbers on the list are called the terms of the sequence. So a sub 1, a sub 2, all the way through a sub n. These are the terms of the sequence. And a sub n is called the nth term of the sequence. Okay. We did this, and now we've just got a couple more topics, a couple more things we want to do with sequences. I want to give you a couple of special cases for sequences. We're going to talk about arithmetic and geometric sequences. And then we're also going to look at some patterns, try to find the formula for the nth term whenever we've got either arithmetic or geometric sequences or some sort of hybrid combination of the two. And then we're going to use that to define something called the factorial, n factorial. Okay, so that's the plan. All right, so let's say we've got a sequence, a list of numbers that looks like this. Let's see, we've got 1, 5, 9, 13, 17. And maybe this is the sequence and it's called a sub n. And someone asks you to find a sub 100. Now we could find a sub 100. I'm going to be here a while. I've only got 5. But if I notice what the pattern is to get from term to term, I might be able to follow that pattern out 95 more times to get to a sub 100. Perfectly reasonable, but I don't have all day, right? Sometimes I want to be efficient with my time. Instead of doing that 95 times, I might want to find a formula for a sub n and then plug in n equals 100. So that's going to be our approach here. So I'm going to list these terms and then try to look for a pattern. A sub 1 is my first term. I'm going to list them vertically. It just makes it a little easier for me to see the pattern personally. A sub 2 is 5, a sub 3 is 9, a sub 4 is 13, a sub 5 is 17. Okay, and now let's see if there's a pattern. Ask yourself, how can I get from a sub 1 to a sub 2? And does that pattern repeat itself? If I'm trying to get from a sub 1 and a sub 2 in a certain way, can I do the same thing to get from a sub 2 to a sub 3? Or from a sub 3 to a sub 4, or from a sub 4 to a sub 5? Well, one way that I could get from a sub 1 to a sub 2 is to just multiply by 5. 1 times 5 is 5. Ask myself, well, does 5 times 5 equal 9? No, so that's not going to work. So I've got to try something else. How else can I get from 1 to 5? I hope you said to yourself, just add 4. Okay, that's a good idea. So a sub 1 was 1, and a sub 2 was 1 plus 4. That's good, and that simplifies to 5. All right, question is, if I add 4 to 5, do I get 9? Yeah, I do. How about if I add 4 to 9, do I get 13? Yeah, I do. What if I add 4 to that? Do I get 17? Yes. So it looks like to get from term to term, I'm going to add 4, and then I add 4, and then I add 4, and then I add 4. So I'm adding 4 a whole bunch of times. I say, okay, well, what's the pattern? I mean, I know the next one, a sub 6, I just add 4. And a sub 7, add 4 again. A sub 8, add 4 again. I don't want to go to 100 though, guys. I know, I sound like I'm whining. I am a little bit. I don't want to have to do that 95 more times to get to a sub 100. I'd rather have a formula. Then you could say, find me a sub 1000, and I could find it. And maybe n does go backwards. Find me a sub negative 50. I could find that as well. If I could find a formula for a sub n, I have them all. I have every single number. I just have to plug it in. Somebody has to ask me for it. I decide, and I could plug in the n value and get the number without having to do this adding 4, subtracting 4 so many times in order to get from number to number. So, okay. Given that, we're trying to find a pattern over here. Now, I know every time we simplify, every time we add 4, we can simplify and get these numbers. I don't want the simplified form though. What I'd like to see is a formula that depends on n. So I want to see what happens as I keep adding 4? Like, what is the general form of a sub n? So a sub 2 was 1 plus 4, which simplified to 5. A sub 3 was 5 plus another 4. Now, instead of looking at it like this, I'm just going to cross that out for a minute. Even though it's true that that equals 5, it's not helping me. When I'm finding a sub 3, I'm just taking a sub 2, which I just had, and I'm adding another 4. Well, that is the same as 1 plus 4 plus 4. That's going to be 2 times the 4, right? I've got 2 of them now. Okay, a sub 4. Well, that was 9, and then I added 4 to that to get 13. Or you could just say, just take a sub 3, which is 1 plus 4 plus 4, and then add another 4. Well, how many 4s do I have now? I've got 3 of them. So this is the same as 1 plus 4 times 3. A sub 5 is 1 plus 4 plus 4 plus 4. It's my a sub 4. And I add another 4. So how many 4s do I have now? I've got 4 of them. So this is 1 plus 4 times 4. Now look at this pattern. Do you see it? I hope you see it. Pattern recognition is hard. Teaching pattern recognition is hard. We're going to do the best we can. So a sub 1 just has a 1 in it. A sub 2 has got a 1 plus a 4. A sub 3 is a 1 plus 4 times 2. A sub 4 is a 1 plus 4 times 3. A sub 5 is a 1 plus 4 times 4. So I think I see a pattern. In order to find the formula for a sub n, I want to think about what's staying the same as I go from term to term to term. What do they all have in common? Even this one that looks a little different, that doesn't have any 4s. Maybe I should add a 4 times 0 there. Let's see that. What do they all have in common? Well, look at them. This one has a 1, this one has a 1, that one has a 1, that one has a 1, and that one has a 1. So a sub n is definitely going to start with a 1. And then, what did we do? We added 4. I added 4 0 times, and then I added it once, and then I added it twice, and I added it 3 times, and I added it 4 times. So every time I'm adding a 4, but 4 times what? That 4 is the same for all of these guys. But what's changing? I hope you see that what's changing is what we're multiplying the 4 by. Here I'm multiplying the 4 by a 0. Here there's an implied 1. Here there's a 2. There's a 3. There's a 4. So that's the part that's changing. I need to find a relationship between the part that's changing and the subscripts. Now that subscript is not 0. But it is one more than 0. That subscript's not a 1, but there's a 1 and that's a 2. So when that's a 0, that's a 1. When that's a 1, that's a 2. When that's a 2, that's a 3. If that's a 3, that's a 4. If that's a 4, that's a 5. So if this is an n, what does this have to be? Do you see the relationship between this 5 and this 4? Do you see that this is just 1 less than this? I hope you do. When that's a 4, what's 1 less than 4? It's 3. When that's a 3, what's 1 less than 3? It's 2. When it's a 2, what's 1 less than 2? It's 1. What's 1 less than 1? 0. So the pattern even holds all the way back to that first term. So if this is an n, I want this multiplier to be 1 less than that. So I've got 1 plus 4 times n minus 1. If I distribute the 4, I get this. Simplify, that's 4n minus 3. And that's the formula for my nth term. You might say, oh, Miss Townsend, that was a lot of work. Well, I can give you a simpler version of this, a shortcut, but it's based on what we just did. This is called an arithmetic sequence. The terms of the sequence come from adding the same number to the last term every time. So the nth term is given by the last term, not the last term in the sequence, but the one before the nth term, plus or minus a constant. So in this case, we were adding 4. We did 1 plus 4 gives us 5. 5 plus 4 gives us 9. 9 plus 4 gives us 13. 13 plus 4 gives us 17. We just keep adding 4 and adding 4 and adding 4. And then we looked for this pattern and we did all of this. Okay. You might say, Miss Townsend, what's the shortcut for this? I want a shortcut. I don't blame you. I was looking for a shortcut. I wanted to find a sub 100. Can I find a sub 100 now? Yes, let's do that, and then we'll talk about the shortcut for finding this formula. a sub 100, that's the 100th term on this list, is just 4 times 100 minus 3. So I get 400 minus 3, or 397. That's a sub 100. Okay. Back to the shortcut for 4n minus 3. You're like, I don't want to have to do that every time. I don't blame you. Okay. Notice that we're adding 4 every time. Since we're adding 4 every time, your a sub n is going to be that 4 times n. Because when n increases by 1, when I multiply that by 4, I'm adding 4 to the whole thing. So as n goes from 2 to 3, this is going to go from 8 to 12, so I'm adding 4. 3 to 4, this is going to go from 12 to 16, so I'm adding 4. Since we're adding 4 every time to get from term to term, we have a 4 times n. And then to figure out what this number is, it's almost like I've got a linear equation and I'm trying to find the y-intercept. Ask myself, 4 times 1 plus what will give me that 1 over there? And that's going to be the negative 3. Now you might say, oh, that was a lot of pointing and not a lot of drawing, and you're absolutely right. Let me draw something for you. Let's sketch this. When n equals 1, a sub 1 turned out to be 1. Now this is not a linear function, but the points on the graph, they look like that they're a linear function. If I were to draw a line through the points, they would all lie on the same line. They actually would lie on the line y equals 4x minus 3. But let's see how that plays out. When n equals 1, a sub 1 is 1, so we plot that point. This is the n axis now. This is the a sub n axis. When n equals 2, we get 5. When n equals 3, we get 9. And so on. And it's going to go off the screen. It's going to go all the way up here. But I hope you see that it's a linear relationship, because I'm going up 1, or up 4 over 1, 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 over and over and over and over and over again. So all these points are going to be evenly spaced on this line, given by 4n minus 3. So as soon as I see that I'm adding this 4 every time, I'm adding a 4 to get from term to term, I know I'm dealing with an arithmetic sequence. The number multiplying the n is going to be that 4. So let's do another arithmetic sequence. So let's say we've got a sequence that looks like this. You have 30, 25, 20, 15, 10, 5, 0, negative 5, negative 10, negative 15, and you just keep going. Okay? You might say, is that arithmetic? Well, first of all, it is a sequence. It's an ordered list of numbers. The order matters. Okay, we're dealing with a sequence. Now ask yourself, can I add or subtract the same thing to get from term to term? Well, let's see. What do I do to get from 30 to 25? Subtract 5. If I subtract 5 from 25, do I get 20? Yes. If I subtract 5 from 20, do I get 15? Yes. 15 to 10? Yes. Awesome. Look at that. Hey. And then subtract 5 again, and subtract 5 again, and subtract 5 again. So every time we're subtracting 5. So a sub n is going to be that common, sometimes people call it the common difference sometimes people will label it with the letter D. It's just going to be a sub n, or a sub 2 minus a sub 1, provided that you add the same thing or subtract the same thing to get from term to term. You just take this one and you subtract this one. It's 25 minus 30 is the negative 5. So they call it the common difference. Take the common difference, which is negative 5, and you multiply that by n. And then we're going to have to add some constant. Now when n equals 1, I need to have negative 5 plus the constant equals 30. Well, then I can just solve for that constant. You could call it x if you wanted to. I'm not going to call it x. I think I'm just going to call it 35. So negative 5 plus 35 is 30. So when n equals 1, I get negative 5 plus 35 is 30. Let's try the formula for n equals 2. Negative 5 times 2 plus 35. That's negative 10 plus 35. That's 25. Is that what I have on my list for a sub 2? Sure is. Let's check it out. A sub 3, negative 5 times 3 plus 35. So that's negative 15 plus 35. Add those guys together and you get 20. Is that the third one on the list? It sure is. So this is my formula. I take the common difference, I multiply it by n, and then I'm going to add something so that when I plug in 1, I get the first term. Okay, so that is how we come up with the formula for an arithmetic sequence. And that's an example of an arithmetic sequence because we're adding the same thing every time or subtracting the same thing every time. Here's one that's not arithmetic. Let's say you've got this list. You have 1, 1/3, 1/9, 1 over 27, 1 over 81, 1 over 243, and so on. Are we adding or subtracting the same thing to get from term to term? I'm going to say 1 plus 2/3, or excuse me, 1 minus 2/3 is 1/3. Okay, so the common difference could be negative 2/3. Is 1/3 minus 2/3 equal to 1/9? I hope you said no. So this is not an arithmetic sequence. But I'm looking for a pattern. A sub 1 is 1, a sub 2 is 1/3, a sub 3 is 1/9. The question is, how do I get from term to term? Well, I notice that if I take 1 and I multiply it by 1/3, I get this. If I take 1/3 and I multiply that by 1/3, do I get 1/9? And if I take that and I multiply by 1/3, do I get 1 over 27? And if I take that and I multiply by 1/3, do I get 1 over 81? I sure do. So this is called a geometric sequence. So to get from term to term here, we multiply by the same number every time. So the nth term is the last term times a constant. And the constant is called the common ratio. Typically denoted by the letter R. And you could take any term and divide by the one before it, and that's going to give you the R. I'm just going to use the first two. I take a sub 2 and divide by a sub 1. So 1/3 divided by 1 is 1/3, and that's our common ratio. Or you could have done 1/9 divided by 1/3. Turns out to also be 1/3. Or 1/27 divided by 1/9. So we're just going to take the first two. This one divided by this one, and that gives us the 1/3. And say, okay, well, what's the formula for this? Well, a sub 1 was 1. A sub 2 was 1 times 1/3. I want to write this expanded. This is 1 times 1/3 times 1/3. This one is, multiply that by 1/3, 1/3 times 1/3 times 1/3. The next one, a sub 5 is 1 over 81. I take the last number, 1/3 times 1/3 times 1/3, and I multiply it by another 1/3. I see exponents, guys. I'm multiplying by the same thing every time. We'll see some other examples when we study geometric series later on why these are called geometric sequences or geometric series. But notice I've got a 1/3 to the first, and there's two 1/3s there, so that's a 1/3 squared, and there's a 1/3 cubed, and this is a 1/3 to the fourth. So the nth term is my 1/3. That's what they all have in common. You might say that one doesn't. Well, you could call that 1/3 to the 0. Hey, now they all look the same. They all have the 1/3 as the base, but that part that's changing is the exponent. When n equals 1, my exponent is 0. When n equals 2, my exponent is 1. When n equals 3, my exponent is 2. 4, it's 3. 5, it's 4. What about when it's n? What's the relationship between that subscript and that exponent? I hope you said it's 1 less. Well, 1 less than 5 is 4. And 1 less than 4 is 3. And 1 less than 3 is 2. And 1 less than 2 is 1. 1 less than 1 is 0. What's 1 less than n? I'm going to call that n minus 1. So this is the formula for the nth term of this geometric series, or excuse me, geometric sequence. Now, standard notation for geometric sequences is this. People tend to use a to be the first term. And then r is that common ratio. And this is provided that you're dealing with a geometric sequence in the first place. So you look at the list and you already know that you're multiplying by the same thing to get from term to term. If that's the case, the first one is a. The second one is a times r. The next one is that times another r, so ar squared. Next one is that times another r, ar cubed. The nth term. It's not ar to the n, although that's tempting. Because this was the first term, that's the second term, that's the third term, that's the fourth term. Notice on the third term that's a 2, fourth term that's a 3. It's the nth term. It's going to tend to be an n minus 1. This is provided that a is the first term. And we're starting our counting at n equals 1. So a geometric series, or excuse me, sequence, is a sequence that looks like this. A and r are constants. And this is starting at n equals 1 and going to infinity. So that's an abstract. So let's look at another one, see if we've got another geometric sequence. We've got -6, 9, -27/2, 81/4, -243/8. Now it's a little less obvious if I'm multiplying by the same thing here because I've got these integers at the beginning and then all of a sudden I have fractions. It's probably easiest to see what's happening with the fractions. If I'm taking this 27/2 and I'm getting this, like how do I get from there to there? I think I multiply by another -3 in the numerator and another 2 in the denominator. So that times -3/2 gave me that. If I multiply that by -3/2, do I get that? 81 times -3 is -243. Yes. 4 times 2 is 8. Yes. So we're good. Question is, does it go backwards? Is -6 times -3/2 equal to 9? Well, 18/2 is 9. Yes, that works. If I take 9 and I multiply it by -3/2, do I get -27/2? I sure do. Okay, so that is our geometric, or it is geometric because we're multiplying by the same thing every time. So the formula for the nth term here is the first term times my common ratio raised to the n minus 1. So that's one way of doing this. Now you could have just said, you could have, instead of having an n minus 1 here, you could have an n there, and you could rearrange this so that that was a power of n instead of a power of n minus 1. I'm not going to do that though. Not on this one. Okay. So that's that. That's a geometric sequence because we're multiplying by the same thing to get from term to term. Now here's one that is neither geometric nor arithmetic. But we see this pattern pretty often, so it's important that we make sense of it. So a sub 1 is 1. I'm going to multiply that by 1/2 to get the second term. Now if I multiply 1/2 by 1/2, I don't get 1/6. But is there a pattern? What can I multiply 1/2 by to get 1/6? Do you see that would have to be 1/3? Like, oh, that's kind of cool. 1/2 times 1/3. Don't know how I would represent that yet, but yeah. How do I get from 1/6 to 1/24? See the 1/4? 6 times 4 is 24. Huh. 1/2, 1/3, 1/4. I wonder if you multiply this one by 1/5 to get this one. What's 1/5 times 1/24? Well, 5 times 20 is 100. 5 times 4 is 20. 100 plus 20 is 120. I think that's right. Yeah. So we've got 1 plus 1/2, and then we have, or times 1/2, and then here we have 1/2 times 1/3 times 1/4. And here we've got 1/2 times 1/3 times 1/4 times 1/5. For the nth term, the numerator is just a 1, and the denominator is 1 times 2 times 3 times 4, all the way up to n. Because when that was 5, the last denominator was a 5. And when that was a 4, the last denominator was a 4. And that's a 3, the last denominator is a 3. And that's a 2, that's a 2, and so on. This pattern comes up so often. It comes up in accounting problems a lot. I didn't say accounting. I hope it didn't sound like accounting. Counting problems, like the number of ways we can arrange flowers and things like that. Number of ways we can put people in certain seats, organize things. This is called factorial. N factorial looks like n with an exclamation point after it. That's exactly how we write it. Means to start with n and then multiply by 1 less, and then multiply by 1 less until you get to 3 times 2 times 1, provided that n is greater than 3. So like 5 factorial is 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. And it's just defined this way. It's defined in terms of something called the gamma function. I'm not going to get into it here. But 0 factorial is 1. So this is actually 1 over n factorial. That's our formula for a sub n here. Now sometimes when you are doing these problems, you have neither an arithmetic or geometric sequence. You might not have anything that involves a factorial, but there might still be a pattern. And usually you can break down that pattern into multiple parts. Part of it arithmetic and part of it geometric. So here is an example where we see something like that. I've got 3 over 4, 5 over 9, 7 over 16. Actually, I've got something that's not geometric or arithmetic, but there's a pattern that we might recognize. Oops. And it keeps going. That's why we put those little dots there to indicate that it goes on forever. Okay. So first thing I notice, in the denominator, I've got squares. That says 2 squared, 3 squared, 4 squared, 5 squared, and 6 squared. So I'm going to write that down. 2 squared, 3 squared, 4 squared, 5 squared, and 6 squared. Okay, there's definitely a pattern there. I can make sense of that in just a little bit. We know a sub n is going to have something squared in the denominator. Okay, now let's look at the numerator. Just focusing on the numerators, just this part. Am I adding the same thing every time to get from term to term, or am I multiplying by the same thing every time to get from term to term? Those are the simplest cases. 3 plus 2 is 5. 5 plus 2 is 7. 7 plus 2 is 9. 9 plus 2 is 11. So I am adding 2 each time to get from term to term. That's nice. So let's see. For our first term, we had a 3. So that was a 2. A 2 plus a 1 would give me a 3. Now, if I took the last term and I added another 2, that's going to be 2 times 2 plus 1. Is that 5? Yeah. If I add another 2, isn't that 2 times 3 plus 1? Because I've added 2 3 times. And then if I add 2 again, well, that plus 2 is just 2 times 4 plus 1. Because I've added 2 4 times. Now I want to add 2 5 times. And let's check. That's 3. 4 plus 1 is 5. Good. 6 plus 1 is 7. Good. 8 plus 1 is 9. Good. 10 plus 1 is 11. Okay. So I think this works. Now, in order to figure out what my pattern is, I need to think in general. I want to write down everything that's exactly the same from term to term, and then I want to think about what's changing. Parts that are the same. They all have a plus 1 in the numerator. They all have a 2 times something. And that something is changing. Now I'm going to highlight, and then in the denominator I've got something squared. 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and I have something squared. And that something is going to be related to the nth term. Okay, so now that's what's staying the same from term to term. Now I want to look at what's changing and how the parts that are changing relate to these subscripts. So that's a 1 when that's a 1. That's a 2 when that's a 2. That's a 3 when that's a 3. That's a 4 when that's a 4. That's a 5 when that's a 5. So what should that be when that's an n? They're the same. So if that's an n, that's got to be an n. Okay. Now let's look at the denominators. When that's a 1, that's a 2. When that's a 2, that's a 3. When that's a 3, that's a 4. A 4 and a 5. When that's a 5, that's a 6. So this is just one more than that. So if that's an n, down here I think we have to have n plus 1 squared. So that's our pattern. We're good to go. And we found a pattern for the nth term. So let me see. Let's go back to our original notes. What were we trying to do in this video? We wanted to talk about factorial, and we did. 7 factorial means you start with 7 and multiply all the way down. Okay, we said a sequence is an infinitely long ordered list of numbers. The order matters. We also said it's a function defined on a set of integers, starting with a particular integer and then moving forward. Terms of a sequence, those are just the numbers on the list. The nth term of a sequence, it's the nth number on the list in general, as a formula, generally. Arithmetic sequences are sequences that you get, or where you get from term to term by adding or subtracting the same thing every time. Geometric ones are ones where you multiply by the same thing every time to get from term to term. When we first started looking at these, we had some concrete examples. We looked at the first few terms of a sequence. If you're given a formula or a recursive definition, you just use the definition. Now, sometimes you have to work backwards. They give you the list of numbers and you have to find the pattern. We used our knowledge of arithmetic sequences and geometric sequences, and then we talked about factorial in order to find that pattern. And so keep those ideas in mind as you do the homework. This is a little abstract, but I hope that you'll like this chapter. It's different, probably, from anything you've ever studied before. But I think it's fun. I hope you think it's fun too.